plus alpha times the total terms and beta times the total terms here. And now apply the Stirling approximation on this one, because Nn for the fermion case is also a great number, a big number. And this is equal to the first term minus Nn log Nn, and minus is there in the Stirling approximation, but this minus and this minus will multiply and it will become plus, and it will be Nn minus. What about this one? Again you will apply the Stirling approximation on this one, and it will be log, it will be dn minus nn log of dn minus nn, and minus and it will become plus, and dn minus nn here, and plus the alpha terms and plus the beta terms here. So this is our equation now, and now we will apply the curly G over curly N on this one. And this is equal to 0. Curly G over curly Nn. So what about the first term? The first term is constant, so it goes to 0. Then the second term. And the second term you apply, minus is here, so apply the product rule with respect to Nn. First function into derivative of the second function is 1 over Nn. Then plus and second function and derivative of the first function is 1. This is done, and now here again minus, you will apply again the product way, and here first function, which is dn minus nn, divide by the derivative of this one, which is dn minus nn, and plus, then log of nn means log of dn minus nn, because this is the second function, and now derivative of this one, so it is minus nn, so minus 1 comes in here in a product. And then it will be the next term. It is, this term is done, and plus this one is 0 and this is minus 1, so minus 1 plus alpha, and with alpha this constraint is multiplied, so it is minus 1. As in the previous we did this plus beta, and it is, beta is minus en. So this is our final expression, which is equal to 0. Right? Yes. This one? Okay. So 0 and this is, and we are having plus 1 here, minus here. It's right? Okay. Now look here, we are having some cancellations. So let me go step by step not to skip the terms. This is minus 1 minus log of nn plus 1 minus, this is minus 1, and minus 1 minus is this one. So minus log nn and minus is this one. So it becomes plus log dn minus nn, and again minus 1 here, minus alpha, minus beta en, and this is equal to 0. Is it right? So now do the cancellations. Minus 1 cancelling with plus 1 here, and we are having this one is, let me check. minus log, this is minus 0 and minus 1 and then minus log nn, and then this one is plus 1, so this is plus 1. And this plus 1 is cancelled with this 1 here. We are left with this one and this one. So let me simplify this one. I can write this one log dn minus nn by log nn. So this is log dn minus nn divided by nn, and this is equal to alpha plus beta en. Right? Now taking again the exponential on both sides, so this will come out to be dn minus nn divided by nn and equal to e to the power alpha plus beta en. And now again we want the terms in nn, so this will be equal, if I do multiply this nn with it, then I will get that this implies that dn minus nn is equal to nn e to the power alpha plus beta en. And now if I move this nn on this side and I take nn as common, then it will imply that dn is equal to nn as common e to the power alpha plus beta en plus 1, and it's common, right? So in terms of nn, this will be equal to dn over e to the power alpha plus beta en and plus 1. Now if I look at these two, like this one is, we call for the fermions, and for the fermions we are, you remember about the fermions that it was, you can say, having overlapping wave functions, and the wave functions were antisymmetric. For the bosons, you were again having the overlapping wave functions, but they were symmetric. While the classical particles, the identical particles, they have to do nothing with the quantum mechanics. So here, if I look at this result, this one, then I know that dn means the number of states, they are much, much greater than 1 here. So if this number is very, very big than 1, then it means you can skip this minus 1. It will not matter that much if you ignore this one, and your nn for this kind of distribution will come out to be dn over e to the power alpha plus beta en minus 1. So look here to the difference between them. This is the statistic which we call the Fermi-Dirac statistic, which we call the Fermi-Dirac distribution. And we write it is Fermi-Dirac distribution. And from the history point of view, Enrico Fermi and Paul Dirac, they independently derived this thing. It is a fact that Fermi did it earlier than Dirac, but it is called as Fermi-Dirac distribution. About this one, the Bose-Einstein statistics, Bose-Einstein statistics are distribution. This distribution by the then Bose, the Indian scientist, he derived this distribution. But due to some complexities, he had some correspondence with the Einstein. And then Einstein just finally wrote the last expression, means just help and that one. And Einstein named it as Bose-Einstein distribution or Bose-Einstein statistics, right? And from here, the term means the field of physics which generated the Bose-Einstein condensation. It's a very active research field and lots of people are doing research in this one. So this one, when we come to the distinguishable particles, we call them the classical particles. Then this is the Boltzmann and it is Boltzmann-Maxwell distribution or Maxwell-Boltzmann distribution. So it is up to you, whichever you make first. Usually it is termed as MB distribution. So this is Maxwell-Boltzmann distribution or statistics. In short, we call this one as the MB statistic, Maxwell-Boltzmann statistics. This one we call in short is the Bose-Einstein statistic, BE. And this one we call in short is the Fermi-Dirac statistic, FD. Right? So look here to the two. This one, Dn here and Dn here. So they both are the same here in the numerator. In the denominator, the only difference between the Fermi-Dirac statistic and the Bose-Einstein is the +1 and -1. Both of these statistics, in the limiting cases, when we consider the number of particles to be much big, the density of states to be much big, are means that these are states, not the density of states, these are states. If I divide this one by dn, then the number of particles divided by the number of states, and it will come out to be the density of states. So it will be like this. If I divide that one, and I define it as small n of energy E. It's a function of energy because here I am having energy. And then this is Ne and this is equal to Dn means Nn divided by Dn. So I define it as the density of states, means the number of particles per number of available states. Then this thing is equal to 1 over e to the power alpha plus beta and En, right? En. Similarly, the density of states this is for the Maxwell-Boltzmann distribution, and the density of states for the Bose-Einstein distribution, Nn over Dn, will be 1 over e to the power alpha plus beta En, and this is -1, and for the Fermi-Dirac distribution, this will be 1 over e to the power alpha plus beta En plus 1. So this is for the Bose-Einstein and this is for the Fermi-Dirac. Now as we have got these distributions, like this is the density of state for the Maxwell distribution, for the Bose-Einstein and for the Fermi-Dirac. Now we will point out that what are our constants. Like we have used one constant, the Lagrange multiplier, which is alpha, and the other constant is beta. Now look here, that what will be these constants? The very first one, let me explain here. If I explain it here or here, they are the same thing. Look here. This is aided with, means first here, this is a number. The density of states is a number. So if you are having number on this side, then number should be on the other side as well, from the dimensional point of view. So this means it's a number. Now look here, the numerator is a number. It means the denominator should be a number. So this denominator is a number. If I look in the denominator, then plus 1 is a number. Then it means this exponential alpha plus beta en should be a number. And you know it is exponential. So the exponential domain here, whatever is in the power of the exponential should be a number. Otherwise it will be dimensionally wrong. So alpha plus beta en should also be a number. Alpha plus beta en should also be a number. Now look here. Whatever the dimension of beta en will be, these will be the dimensions of alpha as well. Because these two are being added. And when two things are being added, it means they are having the same dimensions. So whatever the dimensions of alpha are, the dimensions of beta en are also the same. And now here comes the twist. Alpha and beta en, they are of the same dimension. Now alpha is a constant. Look here, en. We have considered alpha as a constant and beta as a constant. We have no, you can say, some restrictions on them. They are just constant. So what does this mean? That beta en, it should also be dimensionless. As alpha is a constant and it is dimensionless, it is just a number, then this one should be dimensionless and it should be a number as well. Beta en. So what does it mean? It is, if beta is just a number, then it means this should have the dimensions of energy. Because we are sure about this one, that this is energy. Right? So how this thing is possible? This is possible means for this one to be a number, it means that the beta dimensions are 1 over energy dimensions. Right? Means beta should be in 1 over en dimensions. 1 over energy dimensions. Otherwise it will not give a dimensionless thing. Right? And due to these, you can say, discussion, this beta is related to the temperature. Okay? Beta is related to the temperature, and the energy which is associated with the temperature is called the thermal energy, where Kb is the Boltzmann constant. T is the temperature. Boltzmann constant multiplied with the temperature, the dimensions of this kBT comes out to be of energy. And we call this as thermal energy. And what about alpha? Alpha itself means alpha here. So what about alpha then? Because alpha plus beta en is giving you this. If the beta dimension comes out to be 1 over energy, then it means alpha should be dimensionless. Because alpha plus beta en is dimensionless, and this gives you that we define another quantity which we call the chemical potential, which is mu as a function of T. Chemical potential, and I will explain you what is chemical potential. Mu of T is equal to minus alpha times kBT. So now, if this is mu of T, then alpha is mu of T divided by kBT. Mu of T is having the dimensions of energy. Alpha is dimensionless. kBT is of energy, so it means energy and energy on both sides. If I divide this one by kBT, then it becomes dimensionless. So from here I can write that this implies that alpha is minus mu of T over kBT. Means beta is 1 over kBT. Alpha is 1 over kBT. But here is another term which just make it a number, which just make it dimensionless. Mu of T, the chemical potential. We define the chemical potential is that it is determined by the number of N valence electrons that you have, which occupy the levels. You know that when you are filling up the states with the number of particles, what is changing with it? The energy of the system changes, right? But it is not, means for example, in one level, if you are having the number of particles depend which distribution you are talking about, but means the energy may remains with the addition of particles, it remains the same. Like many particles are having the same energy, but when you will change the number of particles, the chemical potential will change. You put one particle, another, and chemical potential will be changing. So for this, let me now write some approximations in this one. And the approximations are, if I do write here chemical potential, then chemical potential, if you take the chemical potential at T equal to 0,